Hello, welcome back to Piers Rocks. Today I want to get a USB version of One ROM working. Why USB? With One ROM USB I can plug it into my PC, go to this web page, select the device, erase and program it in about 5 seconds, disconnect it, put it into my retro system, turn the retro system on, and I'm done. Before we get into today's video, I came back from VCF Midwest with a handful of spare One ROMs. So I'm selling them on my online store and on eBay. And I'm prepared to ship them practically anywhere in the world. So if you want to get a One ROM, now's your chance. I'm selling them for slightly above cost price just to cover my selling fees and handling any returns and so on. I'm afraid shipping prices will be relatively expensive wherever you are. That's just the reality of shipping things internationally today. But if you've been waiting for a One ROM, don't hang around because there's only 12 up on my online store. If I sell out this batch really quickly, I might get another batch fabbed and sell those as well. So why am I adding USB support to One ROM? Well, the main reason is ease of programming and ease of use. I'll be continuing to develop and support the serial wire debug version of One ROM because it will end up having a bunch of more powerful features like the ability to modify the ROM that's being served dynamically while the ROM is actually being served, unlike the USB version. However, I think for most people, particularly those people who are not particularly interested in doing fancy things with their ROMs, they just want a replacement ROM for their particular system, USB will end up being a much more useful and easy to use interface for programming One ROM. Now you might ask, why didn't I support USB from the get-go on One ROM? The main reason, to be honest, is I hate hand soldering small USB connectors. But this particular board was assembled by JLC. They include assembling micro USB and USB-C connectors as part of their cheapest PCB assembly service. So I went ahead and laid out a new version of One ROM with a micro USB connector. First of all, we'll take a look at the schematic. So I've added this section to the schematic, and that includes a micro USB connector here. You may be wondering why I've gone with micro USB rather than USB-C. The reality is that micro USB connectors are slightly smaller than USB-C connectors. It's a few less square millimeters that I need on the PCB, and I thought that was going to be important for this design. I've added electrostatic discharge diodes here, and then the data lines go straight into the microcontroller. The traces here are really short. I've added the ability for One ROM to be connected to a host system and be powered by a host system, and also be connected into USB and get 5 volts from USB simultaneously with these Schottky diodes. So this stops either the host being backfed by the USB supply, which would probably be too much for the USB supply, or the USB supply to be back powered by the host, which could be a really bad thing. So this design should be safe to be plugged into USB at the same time that One ROM is connected into the retro system. And then I've also added an oscillator to the circuit. If you're familiar with One ROM, you've watched some of my previous videos, you may know that I've gone ahead without an external oscillator, an external clock with the STM32 microcontroller. I've had to add an external oscillator for the STM32 USB design, which is what we're looking at here, because while the STM32, well, throughout its entire temperature range, it has a tolerance, its internal oscillator has a tolerance of about plus or minus 4%. Actually, within a temperature range you're likely to be using One ROM at, it's probably more like plus or minus 1 to 2%. That's fine for the application that One ROM is being used for, but it's not fine for USB. USB requires much tighter tolerances on the USB clock. So I've added this external 12 megahertz oscillator to One ROM, to the STM32 version of One ROM, so that it can support USB, and obviously it's got a couple of small capacitors there as well. So now we're looking at the microcontroller itself, and this is the STM version of One ROM. I've only added USB to the STM version at the moment. I'll probably add it to the Raspberry Pi RP2350 version in the future if I can squeeze it onto that circuit board. So there's really just 3 more connections that are required into the STM32. There's VBus, which is 5 volts from USB, that allows One ROM to sense when USB has been plugged in and voltage has been applied to that pin PA9. And then I've got the two data lines coming into the STM32. So relatively small additions to the circuit board required for USB support. It was a bit of a pain to lay out though. Let me show you the new USB design against the old SWD design. So on the left hand side here we have the serial wire debug version of One ROM. This is revision G. And on the right hand side here we have the USB version of One ROM, revision H. The main difference obviously is that the serial wire debug programming header has been replaced by a micro USB connector. There's a few other changes at the bottom of the PCB here. I've taken the status LED and shifted it over to the left hand side of the board, and then I've squeezed in both the electrostatic protection diodes and the Schottky diode that the USB's power supply is coming in through down here. On the top of the PCB, I've had to take the voltage regulator and squeeze it over to the left hand side. That gives me enough room for my 12 MHz crystal and the two 33 puff capacitors that are required. I've got the Schottky diode for the host's 5 volts to pass through, and then there's a few other components like this one that I've had to just move around just to make everything fit. At this scale, it actually looks pretty easy. It probably wasn't as difficult as the RP2350 layout to add USB to this PCB, but it's all pretty tight, and I'm still not convinced that I can actually get a USB-C connector in here. What I might be able to do is just take advantage of this space here and this space here, shift everything including the STM32 just up just a smidge, maybe a millimeter, and that will give me a little bit more room here, and then I can fit the larger USB-C connector on the bottom here. No promises. I may not bother with this. I think a micro USB version is perfectly sufficient for One ROM. We should take a look at the bottom of the PCB as well, because I've moved the programming header to pads on the underside of the board. So we've got the two serial wire debug, the clock and the DIO lines down here. I've obviously got the voltage lines down here. I've got the clock, the test clock output. Probably most importantly, I have the STM32 boot zeros and a 3-volt pad exposed next to each other. With the STM32, if it ends up being bricked or otherwise getting into a bad state, then you need to boot it with B0, boot 0 being pulled high. And in fact, when a brand new board with an STM32 arrives, like this one, there's nothing running on the STM32 at all. When you power it on, there's no bootloader that executes. There is a bootloader in the ROM of these devices, but it's not executed by default. The core is just locked up. So you can either program it with serial wire debug in the locked up state, or you need to pull boot 0 to 3.3 volts and then power the device on. That then causes the STM32 to execute its bootloader and put it into DFU mode, device firmware update mode. We're going to hear about DFU quite a lot in the remainder of this video. So when first programming one of these USB One ROMs with the STM32 microcontroller, you have to jumper these two pads together with a flat blade screwdriver or metal tweezers or something like that. And I'll show you the process in a second. I've actually laid out a slightly tweaked version of the USB design, version H2, which I've not had fabricated yet, so I've not tested this version. And I've stuck vias in front of, in the middle of the boot 0 and the 3.3 volt line, so you can get sharp metal tweezers in there much more easily, because frankly it's a bit of a faff jumping the bare pads, as you'll probably see when I show you that in a second. I've also put vias in the middle of the serial wire debug pads. I couldn't put vias anywhere else because the trace is on the other side of the board. So here's the USB version of One ROM under as much magnification as my camera setup can muster. Obviously got a US quarter next to it for scale. We've got the micro USB connector down at the bottom of the board here. We've got the crystal oscillator here. We've got a Schottky diode here, Schottky diode there, the electrostatic diodes just up here, this tiny 6-pin package here. This was all fabbed by JLC under their cheapest fab service. On the other side of the board, we obviously have the debug and programming connections here, and it's these two pads here next to each other which are boot 0 and 3.3 volts, and these need to be jumpered together for initial first time programming of the device. From that point on, once we've got USB supporting One ROM firmware on the device, we shouldn't ever need to jumper these two pads together again. If there's a programming problem, we end up bricking the device, we'll need to, but otherwise the firmware on board One ROM will detect when USB is connected and drop the device into DFU mode for further programming. So I have a micro USB connector plugged into One ROM, but the other end isn't plugged in, right? So I'm going to jumper boot 0 and 3.3 volts and then plug it in. And on the console, we should see the Linux PC detect an STM32 in DFU mode. There we go. That was first take. It's a little bit fiddly, but with a bit of practice, I can get it done first or second time with these tiny little pads. So this One ROM is now ready for its initial programming. Next thing we'll do is take a look at the firmware modifications required to add USB support. So what's the firmware actually going to do? Well, the STM32 version of One ROM doesn't have enough horsepower to be serving a USB stack at the same time as serving the ROM bytes. The RP2350 version will do because it's a dual-core processor. But with the STM32, we have to take a simplified approach to USB. And what I've decided to do is, by default, when One ROM boots, so if it's installed in the Commodore 64 behind me or the PET over there, it will obviously start serving ROM bytes, and it typically does that within 1.5 milliseconds of boot with the STM32. If USB is connected, if the STM32 microcontroller detects 5 volts from USB in pin 9, then it will trigger a reboot and enter device firmware update mode, which we saw are triggered using the boot 0 jumper, but it's going to do it all in software without requiring that pad to be jumped. And that means that probably within a few milliseconds, the device should be serving its USB stack and can then have its firmware updated. This will obviously stop its ROM byte serving algorithm while USB is connected. So the flow is either take a One ROM that is not plugged into a host, plug it into USB and program it, or if you have a One ROM installed in a host, you should be able to safely plug in USB into that. It will stop serving ROM bytes, so may crash the host system. You can reflash it using the STM32's device firmware update mode over USB, and then disconnect from USB, and One ROM should at that point start serving bytes. So the code that actually does it is spread around a little bit within the firmware. First thing that's important to do is actually set up the USB interrupt. So this code here is first setting an internal pull down on pin 9 where the USB 5 volts is connected into, so that we don't get any false signals on it. And then it's configuring an interrupt to fire if that pin gets pulled high. This code here is the actual interrupt handler itself, and that's just calling the enter bootloader function. Enter bootloader is doing two things. One, it's setting up 4 bytes in the STM32's RAM to a particular magic value, and then it's resetting the ARM core. As a result of resetting the ARM core, as soon as the STM32 microcontroller has restarted, the first function of my code it calls is the reset handler. This normally sets up RAM for One ROM's firmware. But the first thing that it now does is it checks whether that particular area of RAM is set to that 4-byte value that we just set it to. And if it is, it enters DFU mode. And the way it enters DFU mode is essentially the same way that the STM32 enters DFU mode if you pull the boot 0 pad high. It causes the device, instead of booting from the firmware that's been flashed onto it, it boots from its ROM bootloader, which starts serving the USB stack. That's then detected by the USB host, and you can reprogram One ROM. Now we'll build the USB firmware for the device, and I'm specifying the hardware revision to be version H of the 24-pin version. This is an F446RE STM32 microcontroller, and I'm going to put a stock C64 character ROM on here. So I run that make command and it builds the firmware, and we can go and check it's output the information about the build. So for example, we can see it's got the right MCU configured, but really importantly, it's detected that USB DFU mode needs to be supported. So that's compiled into this firmware. So that's good. We also now create an additional binary as part of building One ROM. And as well as the .elf and .bin files that we previously created, we also create a .dfu file. This can then be flashed by the open source DFU util to the STM32 that we have on One ROM. Right, I'm now going to flash firmware to this One ROM. And this has never had One ROM firmware flashed to it at all. This core will be sitting in locked up mode right now. It is powered on, but it's not in boot 0 mode. And the way you can tell that is this LED is not on. It would be on faintly if it was in the STM32's boot 0 or DFU mode. It would be on strongly if it was in One ROM waiting to serve bytes. And I'm going to turn it over. I'm going to jumper the two pads that need to be jumpered. I'm then going to plug it in again, and I've got a separate window up, so I've seen it has detected the One ROM device. It has detected the STM32, and now you can see that the LED, if I shield it, is just on faintly. You may or may not be able to see that on camera, but this is now ready for programming, so we'll program it. Okay, we're ready to flash now via USB. We need to run make followed by DFU flash. All of the other arguments here need to remain the same. So we're in bootloader mode, we're in DFU mode. I can flash One ROM to this device for the first time. So it's building the firmware again. Now it's erasing the device, it's flashing the device, and it should now be running One ROM. So DFU util has successfully flashed the One ROM USB firmware to this device. Next thing we need to do is see if it actually works. Okay, so this is the programmed One ROM. It now has the One ROM firmware on it, but it's still in DFU mode because we just programmed it. If I disconnect it from USB, the LED goes out, and then if I plug it back into USB, it receives power again. And the LED is the same brightness that it was before. This means it's re-entered DFU mode. That's correct because the One ROM firmware that we just installed has the interrupt to detect if it's being powered via USB, and if so, drops it into DFU mode. If One ROM's USB support wasn't working, then it wouldn't have dropped into DFU mode. It would actually be in One ROM byte serving mode, and this LED would be much brighter. To do further testing of this though, we need to stick it into a host and see that I haven't broken the existing One ROM byte serving function. So you just need to give me a couple of minutes while I solder some legs onto this One ROM, and then we'll test it in the C64 that's sitting behind me. The other thing that is going straight into DFU mode when I plug it into USB mode means is that it no longer needs to be physically jumpered in order to flash firmware on it. So as I said, there's a first time programming operation for each USB One ROM where you need to jumper boot 0 to 3.3 volts. But once it's got USB supporting firmware installed on it, as long as it doesn't get bricked, then it can, from then on, it can be reprogrammed just by plugging it into USB. And that's now working. So I've soldered legs onto this One ROM, the USB One ROM that we've programmed a C64 character ROM onto. I have a C64 here with no character ROM installed. The screen is just showing garbage because there's no character ROM. Everything up until now in the video I tested already, so I was fairly confident it was going to work. I've never tested a USB version of One ROM in a host before. I've never tested the actual byte serving functionality, so this is a first for me. So I'll turn off the C64, I'll install One ROM, and we'll see if it works. No, it doesn't work. And I have no idea why. Actually, I have a sneaking suspicion why. It's currently in DFU mode. So I can see that the LED is lit dimly on this chip rather than lit brightly. So for some reason, the USB interrupt has triggered and it's in firmware update mode rather than ROM byte serving mode. So I probably got a bug in my firmware. So I think I've tracked down at least one of my problems. Looking back at the schematic where I have both the power supply from the host, the Commodore 64 in this case, and from USB coming through Schottky diodes to supply the main 5-volt rail for One ROM.
I think what I'm seeing is as a result of too much reverse leakage through this Schottky diode here, the MSK4005 on the USB rail. I've measured PA9, which is where VBus connects into, to sense whether USB is connected. And even without USB connected, I'm seeing 2.2 volts on that pin, which is almost certainly being interpreted as a logic high by the STM32, so it thinks that USB is plugged in. I did look at the datasheet for the MSK4005. The main reason I chose it was because it's very, very small and JLC are prepared to fab with it. But the datasheet implies that the sort of temperature that I'm looking at and the voltage I'm looking at, I should be seeing about 10 microamps current leakage, which should be around 0.4, 0.5 volts on VBus. I'm actually seeing 2.2 volts. So perhaps these MSK4005s are behaving differently from the datasheet. Maybe I've read the datasheet wrong. But I've put an external pull-down resistor on VBus here. This is a 9.1k pull-down. It's just what I had lying around. And we get progress. If I turn the C64 on, while the USB connector is plugged in, there's nothing plugged in on the other end. And the One ROM is serving some data to the character ROM on the Commodore 64. Don't know how well this comes across on the camera, but I'm seeing at least the first 3, possibly the first 4 bytes of every character on every line being served, but then the rest of the lines are garbage. That might be a problem with this particular USB design. It might be a problem with the board that JLC fabricated. So the next thing I'm going to do actually is I'm going to get the oscilloscope on the remaining data lines D3 through D7, and see what I see on those lines. Well, it's definitely a design or firmware flaw, because this is a different USB One ROM that's now installed. It's got the same pull down to prevent One ROM from detecting USB voltage, but I'm getting the same behavior. I'm getting the first maybe 3 bytes of every 8 bytes properly served from the character ROM, and the remaining ones are not being properly served. Behind me, I have a non-USB version of One ROM in there, but the version of firmware that I've been adding USB support to. And we can see that there's these strange lines still down the screen. Now, if I switch back to the last known good version of One ROM, and I reflash this device, it needs to rebuild everything here, so it takes a little bit longer than normal, but it's erasing and reprogramming the character ROM. It works. So the problem is in my development code. So I need to track down what I've done wrong. I think I found my bug. This code here is the code that's actually executed in the main ROM byte serving loop. This sets data pins to output mode when we want to actually serve a byte. And this sets the data pins back to input mode when we want to stop serving a byte. And previously the code stored a half word from the output mask register to the mode register. So this is essentially taking this mask, applying it to this hardware register, which turns the appropriate data lines to serve bytes to outputs. This does the same thing in reverse. And I was doing a store half word previously, and I thought I needed to change it to store a byte here, because I want to make sure I don't affect the top 8 bits of GPIO port A, because the bottom 8 bits are the data lines, but the top 8 bits include the USB ports that I'm now actually using. And I was thinking, well, previously I was using a store half word. That's going to store 16 bits. So it's going to affect all 16 bits of the GPIO port A. Now I just want to affect the bottom 8 bits. That's all well and good, but an output mask or the mode register has 2 bits for every port. So port 0 is the first 2 bits, port 1 is the next 2 bits, and so on. So by storing a half word, you're storing 16 bits, so you're affecting 8 GPIOs. 8 GPIOs is how many I want to affect, because I've got 8 data lines. And now my code is only storing a byte there, so it's only turning the first 4 data lines into outputs, which is why we see the first 4 bytes of every 4 bits of every character properly served, and the last 4 bits are being incorrectly served. So this is just a bug. I just need to change these lines of code back to how they were, to be storing a half word rather than storing a byte, and then USB will work. That's my theory. Right, so behind me I have the non-USB version, but with the bug version of code. So I will change the store bytes back to store half words, and then we can reflash the code. That should start working. We should see a proper C64 display. Yeah, so we fixed the non-USB version. So now we can fix the USB version. We have different hardware revision, we have a different MCU, and we need to make DFU flash. I also need to plug in the USB ROM. So it's in programming mode. So it's programmed. I'll disconnect USB, turn the C64 on. Hooray, at last, it works. So there are two problems. There's a design problem with the USB board that I'm going to have to fix, which is that the VBus is essentially being pulled up high enough to be detected as USB being connected by the microcontroller, even when it's not being connected. I'll have a think about whether there's any way I can get around that in firmware, but I'm already using the internal pull down and it's not strong enough, so this may require a different hardware revision to fix the problem. And the second problem was just some other change I made to the code, where I basically affected the existing, previously working ROM byte serving algorithm by preventing 4 of the data lines being set but to outputs. And now you can see the USB version is working. I don't think there's a design problem here. I think the problem was I was not waiting long enough for the internal pull down on A9 to settle before testing for VBus on that pin. So this routine I showed earlier, which is setting up the VBus interrupt, the first thing it does is it sets pin A9 it sets the pull down on that pin. Then it sets up the interrupts. I mean, this probably takes, I don't know, 5-10 cycles. It's not very long. And then I was immediately doing this if test, testing whether pin A9 was high. I've added this delay. So this is basically just sitting in a tight loop for, I don't know, 1,000, 2,000 cycles. Maybe, I'm not exactly sure what assembly this produces. This is enough delay for this if test to fail unless VBus is plugged in. So that was the problem. I just wasn't waiting for the pull down to settle before testing the pin. I tried values of 100 and 200 here and they didn't work. They weren't enough of a delay. A value of 500 was enough, but I doubled it to 1,000 just in case there's a bit of difference in behavior between different STM32 microcontrollers. But it's good news because it appears that my H revision USB design actually works, and I don't need to spin a new design to get it to work. So there we have basic USB programming function working on One ROM. You may be wondering why I was seeing 2.2 volts on pin PA9, which led me down that whole path thinking there was a design flaw. I think actually the reason I was seeing 2.2 volts is because I was measuring it after the device had already dropped into DFU mode, and therefore there was no pull down configured on PA9 anymore because the STM32 bootloader doesn't configure a pull down on PA9. There's quite a lot more I want to do with USB support on One ROM. For example, with the current support, I can't actually reprogram the device when it's being powered by the host. I'm not 100% sure why that is. I spent an hour or two trying to track that down, and I think it's just the way the STM32's built-in device firmware update mode actually works with its USB enumeration. So I may have to implement my own bootloader within my firmware to overcome that limitation. But with this support, I've now overcome the initial bootstrapping problem. The first time you get a brand new USB One ROM, you still have to jumper the boot 0 pad to 3.3 volts before you can program it for the first time. But now you can program at least this version of firmware
This will then allow you to program further updated versions of firmware without needing to jump that at all over USB. This also allows me to simplify further the programming of One ROM. So right now you saw I was still using the same makefile process to do a firmware update. That requires all of the different dependencies required to build One ROM, and then building One ROM and then flashing it. I have some cunning plans for actually providing much simpler ways of programming One ROMs in future using this new USB mode. As I said at the beginning of this video, I've got a few spare One ROMs, not the USB version sadly, for sale on my website and on eBay. So look down in the description if you're interested in getting hold of one or more One ROMs yourself. If you've got any questions about One ROM or any comments on what I've been doing in this video, please stick those down in the comment sections and I'll do my best to respond to those. I hope you found this video interesting and useful. If you did, please do consider sticking around. Till next time, rock on.